Question 1. A squid moves through the water by ejecting water out of its body into surrounding water. When the water is pushed out, the ejected water pushes back and thrusts the squid forward. Which of Newton's laws of motion best applies to a squid's movement through the water? A. First law of motion, law of inertia. B. Second law of motion, law of force and acceleration. C. Third law of motion, law of action and reaction. Or D. Fourth law of motion, law of balanced forces. Question 2. A driver starts her car and steps on the gas pedal. The car gradually accelerates to 15 kilometers per hour. A few minutes later, the driver suddenly slams on the brakes to avoid hitting a box in the road. As the car comes to a stop, the driver's body continues to move forward in the seat until it is restrained by the seatbelt. What law best explains why the driver's body continues to move forward when the brakes are suddenly applied? A. Newton's law of inertia. B. Newton's law of force and acceleration. C. Newton's law of action-reaction. Or D. Law of conservation of mass. Question 3. Assume that a 75 kilogram ice skater is on a nearly frictionless surface. What force in newtons would be needed to accelerate the skater 3 meters per second squared? Record your answer and fill in the bubbles on your answer document. Be sure to use the correct place value. Question 4. Newton's third law of motion states that for every action there is an equal and opposite reaction. Which of the following object's motion is an example of the law of action-reaction? A. A person riding in a car without wearing a seatbelt will move forward when the car comes to a sudden stop. B. A motorboat must exert a force of 100 newtons to accelerate a 50 kilogram water skier at a rate of 2 meters per second squared. C. A hockey player skating towards her goal will continue to slide towards her goal if she slips and falls. D. A rocket engine forces gas in a downward direction to launch the rocket upward. Question 5. The table below shows two cars traveling at the same speed down a hill toward a stop sign. What will happen when both cars apply the brakes at the same time to stop? A. Car 1 will require less force to stop than car 2. B. Car 2 will maintain its velocity while traveling down the hill. C. Car 1 will take longer to stop than car 2. Or D. Car 2 will have less inertia than car 1. Question 6. A student jumps off a sled toward the west after it stops at the bottom of a very icy hill. Based on the law of action-reaction, in what direction will the sled most likely move as the student jumps off? A. North. B. South. C. East. Or D. West. Question 7. Modern automobiles are tested for collision safety using models of human beings often called crash test dummies. These dummies are actually quite smart. They are often fitted with sensor devices that can record their motion and force of impact during an automobile collision. Which of the following is true about the crash test dummy when the car is traveling at 80 kilometers per hour based on Newton's law of inertia? A. The crash test dummy is at rest if it is restrained with a seatbelt, but the dummy will travel 80 kilometers per hour if it is not restrained with a seatbelt. B. The crash test dummy will travel less than 80 kilometers per hour if it is restrained with a seatbelt because the dummy's inertia will slow down. C. The crash test dummy will travel faster than 80 kilometers per hour if the car crashes because the momentum of the car will be transferred to the crash test dummy. D. The crash test dummy will continue to travel at 80 kilometers per hour as long as the car travels at the same speed. Question 8. The diagram below shows two different forces acting on a cyclist riding a bicycle. The total mass of the cyclist and the bicycle is 100 kilograms. Based on this information, what is the acceleration of the cyclist? A. 0.66 meters per second squared backward because of the force of the air slows the cyclist down. B. 0.66 meters per second squared forward because the applied force is greater than the force of the air. C. 2.3 meters per second squared backward because the forces are opposite and not equal. D. 2.3 meters per second squared forward because the cyclist's inertia is greater than the force of the air. Question 9. During a demonstration of Newton's laws of motion, a student used the setup shown in Figure 1. The student flicked the index card with a fingertip and the coin fell straight down into a plastic cup, as shown in figure 2. Which of these best explains why the coin fell straight down into the cup instead of remaining on the index card? A. The coin was at rest until the card was removed, so it tended to remain in the same location. Once the card was gone, the unbalanced force of gravity caused the coin to fall. B. Moving the card applied an action force on the card. Since the card was gone, gravity applied a reaction force on the coin. C. The card had less mass than the coin, so a smaller force of gravity acted on the card. The larger force of gravity on the coin made it fall. D. The acceleration of the coin falling into the cup was equal and opposite to the acceleration of the card. Question 10. The masses of 4 vehicles and the net forces acting on them as they enter a highway are recorded in the table below. Which vehicle has the greatest acceleration as it enters the highway? A. Sedan, B. Coupe, C. SUV, or D. Truck?